Okay, since the last time we talked about the edge-restricted minimum for the minisum absolute medium problem, and we observed that the distance function on it is concave piecewise linear with at most two pieces. And when you add up piecewise linear functions of that sort, you end up with a minisum function which has linear pieces, and it's concave because the sum of concave functions is concave. So that's the sort of function you would get. And you can see just from the shape of this that a minimum occurs either at one endpoint or the other one. It is also possible that minimum may occur along the edge, in which case, of course, your function should look like this. That's the only way it can happen. Okay? So interior point minimum are possible, in which case you still have minimum at either this endpoint or that endpoint, as well as possibly in interior points. But the generality of endpoints being supplying a minimum does not change or is not affected by that. Okay? All right. So edge restricted minimum occurs at one or both endpoints of the edge. Under consideration. Okay? Accordingly, the minimum of the function evaluated at endpoint VP, so we're talking about the edge with VP, VQ. Accordingly, the minimum of F evaluated at VP or at VQ, this is the minimum of two numbers. That's as good as the minimum of F when X is restricted to the edge VP, VQ. So the optimization problem involving the entire edge is solved by evaluating the F function at either endpoint and picking the minimum of them. Okay? And of course, since this is true for each edge, then when you look at the entire network, when you want to minimize the sum of weighted distances, the minimum on each edge occurs at one endpoint, which means the minimum of the entire network also occurs at a vertex location. Okay? That's straightforward. That's known as the node optimality or vertex optimality theorem of Hakimi. Proved back in 1964. Hakimi did not state the theorem in this way. Rather, he said that the absolute minimum, the absolute median occurs at a vertex. That's how he stated it. It's incorrect. So the statement simply says that there's at least one absolute median on a vertex location, which does not disqualify edge interior points from being optimal. Okay, there's a minor difference. Nevertheless, still Hakimi's theorem is very important, even though there's a minor portion that needs to be corrected, which is okay. Yes, sure.
In this case,
When can this occur? Good question. What do you think? Well, yes. Now, if all of your distances are like this, when you add them up, it becomes like that. If at least one of them, if at least one of the distances is either this way or the other way, or like a half stop, then it will not occur. So it's a very special circumstance. Do you believe that?
it happens when all edge costs are 0.
Yes, that's a very special case. Well, edge cost, no. There's no edge cost. We have edge lengths in our case, or edge costs. They are all positive by assumption. If you're talking about node weights, the node weights could be 0. I assume they are positive. So in that case, of course, you're not going to have one of these situations. Okay? But what I'm going to do right now is to prove this theorem in the way Hakimi actually conceived it. Hakimi did not talk about concavity of these functions, etc. That comes later. So I'm going to give you a more self-contained core proof, which does not rely on concavity or anything like that. It's instructive because it gives additional insights on what's going on. Except that I'm going to change the notation quite a bit, because if I don't do it, it's just too long to recite on the board. Okay? So when you read the paper of Hakimi, don't be surprised if you see a totally different notation. Okay? Okay, so we consider again the edge-restricted problem, where the objective function is simply the sum of weighted distances. And what I'm going to do is I'm going to partition the demand vertices into two subsets. But before that, let's do the following. Let alpha be the length of the sub-edge VP x as x varies in the edge. So when you look at this and take any vertex Vi, we come into the point x by means of either endpoint Vp or the other endpoint Vq. So I'm going to partition the vertex set into two parts. I'm assuming x is an arbitrarily selected point on the edge. Okay, it's a fixed point. It's arbitrary. So whatever I say here, the conclusion will be true for every x at the end. Okay, so partition the index set of the vertices into subsets IP and IQ, where IP consists of those vertex indices I such that the distance between x and vi is realized by the path going from x to vp and then to vi. So we're talking about this length or this distance being defined by alpha plus the distance from p to I. And so that by assumption that's less or equal the other path length, which is how much? LPQ minus alpha plus dqi. I permit equality, okay, in this one. And I define IQ to be the remaining set of vertices, which means that it's I for which distance between x and vi is defined by the other one, LPQ minus alpha plus dqi, which is by assumption strictly less than alpha plus dpi. Okay? So every vertex belongs either to one of the sets or to the other one, not both. All right. Let me define capital W sub P to be the sum of the vertices of the sum of the weights of the vertices where I belongs to the first subset. And WQ is similar. Okay. Now I've got only two possibilities. Either WP is less or greater or equal to WQ. In the other case, WP is less than WQ. So we're going to prove the node optimality for both cases separately. So in this case, when you look at the function f at x It's by definition Wi dx vi. And if you partition the vertex set into the subsets IP and IQ, then we have Wi dx vi I in IP plus Wi dx vi I in IQ. Now, in the first set, the distances are defined by what? Alpha plus dpi. In the second set, the distances are defined by by LPQ minus alpha plus dqi. So I'm continuing from here. This gives me alpha into the sum of the weights Wi in IP, and over here we have minus alpha times Wi for sum of the weights in IQ. So alpha into Wp, the total weight for the P side, minus the total weight for the Q side. And then I've got some other stuff. That other stuff will be the following: Wi times dpi for I in IP. And for the other part, it will be Wi times LPQ plus how much? dqi. Okay. Now I should make some sense out of this. Okay, that part is pretty straightforward. Over here, what you want to notice is the following. I'm talking about for the case where Vi is such that I is in Q, IQ. Okay? Now, in this case, if you look at this distance, dpi here, and compare that with that one, let's forget this. Yeah, it's not important. Let's just look at a particular vertex. Let's take that distance from P to Vi, and the other one is the portion going from P to Q, that's LPQ, plus the portion going from Q to I. So this one is the length of that arc plus that. So from triangle inequality, what do we know? It's greater or equal the actual distance between P and I. So this one is greater than or equal to dpi. Okay? All right, which means that if I replace each term here by dpi, I would get a greater or equal like that. So when I do that, of course, I get Wi dpi for every I. In other words, IP and IQ, which means you've got I in the set of all possible indices. And what do I know about this part? This is simply the value of the function f evaluated at VP. Okay? So this is equal to alpha times W P minus WQ plus f of VP. Now, what do I know about this part? I know alpha is positive, or at least it's non-negative, unless alpha is 0. Okay. This one, by assumption, WP is greater than WQ, so this part is greater or equal 0. So that we have a non-negative number here. If I drop that, that means the entire thing is greater or equal f of VP. So the conclusion is, when you assume the total weight on the P side of the demands is at least as large as the total weight on the Q side of the demands, then VP is the better choice, or the minimizing choice. Okay? So f of VP, or VP, is a minimizer of f of x for the edge-restricted problem in this case. This is true whenever you're minimizing over x's in this interval for which WP is greater or equal WQ. Now let's look at the remaining case. Of course, by symmetry, you can immediately see that it will be the other way around in the other case. But nevertheless, let's go through the proof. By the way, when would this be an equality? In other words, when would, where am I? Here we started out with f of x, and then we went through some equalities, and then an inequality, another inequality. In order for these inequalities to hold as equalities, what should be true? This should be 0, first of all, which means that if alpha is non-zero, then the total weight on one side should be the same as the total weight on the other side. And what else? And this should also hold as equality. And what does that mean? Then that means this length should be the same as that length, so you have two alternate shortest paths in that case. Okay? So whenever those conditions are fulfilled, actually the interior point x can also be optimal under these conditions. Okay? All right, the remaining case. Well, you can cut this short by simply saying that by symmetric argument, then it's, you know, f of VQ should be the minimizer. But let's do this because we have strict inequality. F of x in this case is going to be, again, summation Wi alpha plus dpi, I in IP, plus summation Wi LPQ minus alpha plus dqi, I in IQ. which is equal to alpha into WP. Well, actually, let's not do it this way. How should I do this? Just a second. Okay, what I want to do is I want to add LPQ, then subtract LPQ inside the parentheses. If you do that, you don't change anything. Okay? So that you can take LPQ minus alpha as a multiplier for the W's. In this case, it will be WQ, because you've got LPQ minus alpha times WIs for that index set. Minus, in this case, you've got minus LPQ plus alpha, so that will take WP. Okay? Plus, we've got summation WI LPQ plus DPI in the first one, plus I've got that one. Now this again is the length of going from Q to P, then from P to I. That's the length of that path. Okay, so for that reason, this is greater or equal distance, the direct distance from Q to I. So that means we have LPQ minus alpha, WQ minus WP, plus summation WI DQI I in the union of both sets, or in I. Yes. This one? It should be what?
Because we use LPQ on the left side and the LPI remains.
Well, I can't change that. This is correct. See, I've got alpha plus DPI plus LPQ minus LPQ. Now that minus and minus LPQ plus alpha is here. So that portion is taken care of. And then I've got LPQ plus DPI, which is here. Okay? That's LPQ. That's a Q. Okay. That's the length of the edge. Okay? All right. What happened now? So let me put these back in. All right. So I've got this now. And of course, this part is f of VQ. In this case, this is strictly larger than 0. This portion is either 0 or greater than 0. Well, for the special case when alpha equals LPQ, which means you're on top of VQ, that would be 0. But for the remaining cases, this will be positive. Okay? Assuming, of course, x is different from VQ. Which means that when you drop this term, this is strictly greater than f of VQ. I think that's instructive to observe the strict inequality or what it causes. Okay? So in this case, no interior point can be an optimizing point. This is strictly better. Okay? So you can notice from all of this is that if I have the total weight on one side strictly greater than the total weight on the other side, then, of course, the end point, which actually is part of the larger weight, is the unique optimizer. That's important. If they happen to be equal, the total weights happen to be equal in balance, then it is possible for some interior points to be optimum. But that requires, where am I? The other proof, okay? Yeah, okay, here. But that requires, if this is positive, then of course you would have to assume this is 0, okay? And so that would turn that into equality. And this, you want that to be also, then you would also have to assume that you've got alternate paths for all vertices, which is a rather strict requirement. And so that's a very unlikely situation. Did you ask the question? Yeah, okay. Okay, so the grand conclusion is the following. Well, it's the node optimality, so you can write it down. At least one of the end vertices always qualifies as an optimizing point. Okay? How do you think Hakimi saw that result? Hmm? Yes, but how did he see it? We always look for an easy way out. He probably solved an example. Normally, that's what happens. Mathematicians solve one example, and from that example, they make grand conclusions. Non-professional people, they solve lots of examples, and from lots of examples, they make sometimes grand, sometimes small conclusions. Okay? So, knowing maths is pretty good because you can do a lot of stuff from a small example. Okay? That's not my conclusion. That's what Ali Nesin says, you know. Ali Nesin is a mathematician. So he had one book. At the beginning of the book, that's what he said. Mathematicians make use of a single example to make theoretical conclusions. Non-math people, they do a lot of examples. And sometimes they make conclusions, sometimes they don't. All right, so here's an example now for the node optimality. It's really nothing interesting. Nevertheless, let me just give this example. The edge lengths are as given on the edges. The node weights are as given on top of every node. So what you do to compute the absolute median is the following. You compute the distance matrix first. And it happens to be 0, 1, 6, 4, 5, 0, 5, 5, 6. Well, actually, let me put down the lower half also. 6, 5, 0, 4, 3, 4, 5, 4, 0, 2, and 5, 6, 3, 2, 0. That's my distance matrix. Then I put down my weights on top of the columns. 2, 1, what else? Number 3 has 3. Number 4 has 1. And this one is 2. And then from that, from those weights, so these are the WIs, you can compute the W J times distance ij. So for I equals 1, you simply compute 2 times 0 plus 1 times 1, 3 times 6, etc. And that turns out to be 33. For the second one, the weighted sum turns out to be 34. Next one, 27. Next one, 29. Next one, 27 again. So you have 2 possible node locations that both qualify as absolute medians. Actually, the term absolute does not make any difference anymore because an absolute median is the same as a restricted or vertex restricted median if you're just interested in solving the problem. Okay?
Don't use the shortest path.
Yes, but it has nothing to do with this now. Okay? We are using, well, did you see something? This is supposed to be the distance matrix, and it does give you the shortest possible distances between pairs of vertices. Is that what you're asking? Yeah. We're not using the lengths. We're using the shortest path lengths. Okay. Somebody asked last time what the order of computations would be for this one. How much would it be? First of all, to generate the distance matrix, how much time do you spend? Well, if you use n cubed, yes. To compute the distance matrix D. Again, you can do that by using either an all pairs algorithm, such as Floyd's, or you can use Dijkstra once for each vertex as a home base. Okay? Dijkstra works in O(n) squared time, and so when you repeat it for each vertex, it will be O(n) cubed. Now, if this is available, then computing these numbers would call for a weight times an entry, and you have n entries here, so that would call for O(n) per row, just computing the objective function. But you repeat that for each one, so it's O(n) squared. So the total effort is this much if D is available already from prior computations. But if you also have to compute D, then of course this one dominates the other one. Okay? Now let's look at the medium problem, the absolute medium problem for the special case of a tree network. Tree networks may naturally occur if you're using rivers, etc., for transportation. But if you're not using rivers, usually when you look at highway systems, they are sparse networks, so you may approximate them by a tree of some sort. Okay? But other than that, this is of mathematical interest because this is a special case, so you want to be able to take advantage of any possible specialties or properties. In this example, I have a tree network. I assume everybody knows what a tree is. Anybody who does not? Okay. So, in a tree network, a tree network is a connected network which has no cycles. Okay. In this one, I've got 7 vertices with vertex weights as listed in the picture. Which one? This one? Okay. 1. Let's just make it 1. All right. When you look at, for example, the edge-restricted problem on 2, 4, you would notice that the sets IP, or the total weight WP, W2 in this case, P equals 2, Q equals 4, and this side has the total weight W, whatever it is. Okay? How much is W2 in this case? Well, whatever vertices you've got here, that's your total for that side. Why? Because in this case, you've got no cycles, so whenever you want to go into a point X from a vertex on this left side, you have to visit V2 first. So the partitioning I sub P and I sub Q is a very natural one in this case. Okay? It doesn't change. All right, so in this case, my set I2 consists of vertices 1, 2, and 3, which means that my total weight is how much? 1, 3, 6. It's 6. What about this guy? It consists of vertex indices 4, 6, 7, 8, and 5. And the total weight will be 1, 2, 4, plus 3 is 7, plus 1 is 8. Did I do it right? Okay. So what is your conclusion? This side is the heavy side, so the edge-restricted minimum occurs here, and it's a unique minimum. Good. Now, let's not stop there. Can you also somehow conclude that the optimum should be, the tree network optimum should be on this side? Can you see that? Well, you should be able to see that because if I pick any point in the interior, it's not as good as that one. If I pick something else here, then the total weight associated with whatever edge is under consideration will include this as well as other stuff. So it will get even heavier. So moving towards here is of no use, really, as far as optimizing. Okay? So you want to be somehow moving from here to possibly inside that one. So when you look at that one, you might want to consider either 1, 2 or, 4, 6 or 4, 5. Which one do you want to pick? Let's pick 4, 4, 5, for example. What's the total weight on this side and the total weight on this side? Well, the total weight on the side of 5 is 3. The other one is how much? 11, yes. So in that case, this one is optimum. Okay? So V4 persists being optimum. What about V4 and what's the other one? V6. W6 would be how much? 4. And this one is how much? 10. So this persists. Well, you immediately see it. Can you somehow utilize this information in a more systematic way? That's the question. Somebody did actually, named Goldman, and he came up with a very efficient algorithm. What he did is the following. Let me just illustrate that, and then I'll let you go. So Goldman gave a tree trimming algorithm which actually computes the median for a tree network very efficiently. The total weight in this case is how much? 14. So what Goldman does is he actually begins with tip vertices, the vertices that have exactly one edge incident. So this one, when you partition it in your head, it will have a total weight of 1 on one side and the remaining weight, which is 13 on the other side. So obviously you want to move your attention towards this part of the tree for looking for an optimum. Okay, that part is gone. Okay, you can just drop it. Nevertheless, that weight is not gone. So when you drop this, you want to account for that as if it's still there. Okay, it's attached here. Okay, so you add that weight to this one, and then you pick another vertex such as this one, a tip vertex, and this is one. So you just remove this again and add the weight of that to that. You don't have to erase these things. You can just cross them out. Okay? And then what else? You look at this one, for example. That's still less than half of the weight. In other words, it's only 4, whereas 12 is on this side. So you delete that. And add that to that. You look at this one, it's gone. You look at that one, it's not going anywhere because it already has, or is it going somewhere? 5, 8, yeah. The total is 8. So this is strictly larger than the rest. So you can simply conclude. But actually, he doesn't conclude here. He actually works these out. Finally, the entire thing degenerates into a single point. So he goes from here to there. Finally, he looks at this one. Again, this one is crossed out. finally you've got this. Okay? So that's single point. What's the efficiency of this algorithm? First of all, I did not use any of the edge lengths. See? The man is intelligent. This works for any kind of tree as long as the structure of the tree is preserved. Okay? It doesn't matter what the edge lengths are. How much is it? You process each vertex once. That's it. O(n). Very efficient.
How about the edges? I mean, in processing every vertex, you might have to process as much as the number of edges because you sum the numbers.
True, true. So you process n-1 edges because a tree network has n-1 edges. Okay? So it's still...
Squared?
No. A tree has n-1 edges, one less than the number of vertices. Well, actually, processing edges in this case is really nothing. You just discard it from further consideration. But you do one addition operation per processing. You add the previous node weight to the one that you moved into. Okay?
But do you also calculate the weight of the rest of the tree?
Not really. You can do that by simply computing the total weight divided by 2. Take the half of the weight. If the vertex that you're considering right now happens to have a weight at least as much as half the total weight, so if the current vertex, the modified weights, possibly, satisfies this. No, capital W is constant. That's the sum of all weights. So in our case, that will be 7. W over 2 is 7. So whenever the total weight happens to be greater or equal half the total weight, you don't discard that. You just stay there. And finally, of course, other things get discarded, and you just stop there. Okay? Actually, as soon as it exceeds half the total weight, you can also stop there. Okay? Okay, we stop here.